You know, I used to be addicted to eating soap, but then I got clean.
Yeah!
So that's now going to get us to shift gears a little bit to talk about what a matrix is. A matrix is just an array of numbers, variables, or a combination of them. And later on, we'll actually be putting functions inside of matrices.
Lord have mercy.
But what we mean by array is that, it's an apparatus that has rows and columns. And this is one way of defining a matrix in a very generic way, albeit. And in each one of these spots, in other words, in any particular row and column, we have what are called entries. The first row, I like to indicate that with R sub 1, and that would consist of all these numbers or expressions, A sub 1, 1, A sub 1, 2, and so on and so forth. Right underneath that is row 2.
Whoa, whoa, whoa.
And right underneath row 2 is row 3, and this goes all the way down to row M. Now, how do I know that's row M? It has to do with the fact that the first thing that's written in that subscript is M. The first column would be this, those consisting of A sub 1, 1, A sub 2, 1, all the way down to A sub M1. The second column will be to the right of that, the third column to the right of that, and we get all the way down to the nth column. And how do I know it's the nth column? It has to do with what they're writing after the explicit number here, so A sub 1n. All right, so all in all of these items that are populated within this rectangular array are referred to as entries.
Oh, yeah.
And generically speaking, we could write an entry as A sub ij. Now, the value of I indicates the row of the entry, and the value of j indicates the column of the entry. So let's get some practice with that. I have a matrix here, and in this example, we want to identify 5 particular entries. The first of those entries is A sub 1, 4. A sub 1, 4 tells us that we should be looking at the number that's in row 1 and column 4. So it might help to mark off the rows and the columns. This would be row 1, this would be row 2, row 3, and row 4. And then this would be column 1, column 2, column 3, and column 4. So it's kind of like a multiplication table where you just cross the row with the column and you multiply, the two numbers that lead off, each row and each column there in a multiplication table. And this one is location, A sub 1, 4. So we want to be in row 1 while at the same time looking in column 4. And the common number that's in both those at the same time is 5. A sub 1, 4 would be the number 5. Does that make sense? Let's do A sub 2, 2. Okay, so we want to be in R2. So row 2, column 2. Okay, and where they meet up at is at the entry 6. All right, I'll have you folks try this out. Go ahead and see if you can identify A sub 3, 4, A sub 4, 1, 4, 4.
Now it's time for everybody's favorite subject.
All right, here we go. Those look good to you guys? All right, so one thing about matrices, they allow us to abbreviate linear systems. And there's a special type of matrix that can be created out of a linear system.
Boy, ain't no way, boy. Boy, ain't no way, boy.
And that matrix is called an augmented matrix. So let me show you how to create an augmented matrix, and I'll explain why it's called augmented and all that jazz there. Our first system has 2 equations and 2 unknowns. If you think about this from a row and column standpoint, since there are 2 equations, there should be 2 rows in our matrix. There are 2 variables, so you might think that there are going to be 2 columns. Well, in an augmented matrix, for something like this, there are going to be 3 columns because there's going to be a column for the constant terms as well. So what I'm going to do is write out a bracket from a matrix notation. And by the way, some of the older school instructors use just large sets of parentheses for the matrices. I tend to use the brackets.
Come on now, dog. Come on, man.
In this first row, what I'm going to do is I'm going to write out the coefficients of the variable x and y, okay, without the variables and without that plus sign there. It's going to be 2, and I'll leave a little bit of a space, a little bit of a gap there for the coefficient of y, which is 1. And I'll do the same using the coefficients of the variables x and y in the second equation. So -4 and 6 is what I'd put there. Now we are going to include the -1 and the 42, but to distinguish -1 and 42 as constants versus coefficients, what we do is we put this large vertical bar. It really kind of represents the equal sign. But that large vertical bar there is going to separate the coefficients from the constants. And the constants are -1 and 42. And this is what we mean by augmented matrix. And it's called augmented because we're augmenting, or we're joining, in a sense, the constants with the coefficients all in one matrix. Okay, and we use this long vertical bar just to tell ourselves, hey, anything on the left-hand side of this is coefficient, whereas anything on the right-hand side of this is a constant. Now, it's important that all of your variables line up in the original linear system. So they line up here. You know, we have x on top of x, y on top of y, and they also line up in the second system. But, you know, if any of your variables are shuffled out of order, you know, you want to make sure that they're all lined up with each other before you throw it into an augmented matrix format.
Every day I'm shuffling.
It's probably not too much of a stretch of the imagination here that this matrix that we're going to write out next is going to have 3 rows, and it's going to be 4 columns by, you know, with the augmentation of the constant terms. All right, so I'll start with the coefficients. The first equation, 3, 7, and -8, and then 4, -1, and 2, and then 2, -2, and -3. Okay, so those are the coefficients, and I'm going to separate these coefficients from the constant terms, which I'll add into the right of this vertical bar. So -1, 16, and 5. And that would be the augmented matrix form of this linear system.